Hi, everyone. Welcome to this talk. Here I'm going to present our paper, Optimizing Global Injectivity for Constrained Parameterization. Mapping triangle meshes into the 2D plane is a fundamental task in graphics and geometry processing. A well-known application is texture mapping, where the map is used to transfer color information from the 2D texture image to 3D surface. Most applications require the mapping to be injective or one-to-one. That is, any two distinct points of the mesh are mapped to two different points in the plane. A non-injective map is not usable in many applications, such as texture mapping. For a map on triangle mesh to be injective, it must satisfy several criteria. The first group of criteria contains the local neighborhood of vertices, edges, and triangles. Specifically, the triangle cannot be degenerate. Two neighboring triangles should have the same orientation, and the sum of angles around the vertex should be 2 pi. The vertices with an angle sum more than 2 pi are called overwound vertices. For the map to be injective everywhere, it has to be free of overlap between any two triangles, even though they are not adjacent to each other. However, an injective map can be entirely inverted, which is also not desirable in practice. In this work, we consider globally injective map that is inversion-free. There are some applications where the mapping is computed under positional constraints. For example, these constraints are used in constraint texture mapping and handle-based deformation. In this work, we take as input a source mesh and a group of positional constraints and try to compute a globally injective mapping satisfying the constraints. There are many methods to compute injective mappings. However, we are not aware of any method that is designed for arbitrary positional constraints. A classical method to obtain an injective map is Tott embedding. However, it requires fixing a convex boundary, and it also doesn't accept arbitrary positional constraints. More recently, there are maintenance-based methods that start from an injective map and deform the map to improve the map quality while preserving injectivity. However, these methods require injective mappings to start with, which are not generally available when there are positional constraints. There is another group of methods that can start from a non-injective map and try to remove all the inverted triangles. However, these methods cannot deal with overlaps, as in overwound vertices or overlapping between non-adjacent triangles. Finally, some methods compute injective mapping, but require changing the mesh structure, such as adding more vertices. In some applications, the change of mesh structure is not allowed. In this work, we propose the first method to compute injective mapping under positional constraints without changing the mesh structure. Our method starts from an initial map that may contain various artifacts, such as inverted triangles, overwound vertices, or even global overlaps. By optimizing an energy, our method produces a globally injective map while satisfying the positional constraints. The core of our contribution is a new energy whose minimization promotes injectivity. Our energy captures both inverted and overlapping area. It's sufficiently smooth to allow gradient-based solvers to proceed, and we proved the energy has theoretical guarantees of injectivity at its global minimum. Next, we'll define this energy and discuss its properties. Our energy utilizes the concept of winding number, which I'll briefly introduce here. Consider a closed-oriented curve in the plane. The winding number at a point is the number of times the curve travels counterclockwise around that point. Depending on the location of the point, the winding number can be integer that may be either positive, 0, or negative. For each region partitioned by the curve, all the points in the region have the same winding number. We introduce another interpretation of winding number that makes it more relevant to our problem. Consider a mesh whose boundary is the curve C. Then the winding number is the number of non-inverted triangles minus the number of inverted triangles covering that point. Based on the 1D number, we introduce a new quantity called occupancy, which roughly measures the area of the plane covered by non-inverted triangles of a mesh. And this quantity is defined as the total area with positive 1D numbers. We can show that for any mesh bounded by the curve, each point with a positive 1D number has to be covered by at least one non-inverted triangle in the mesh. Based on the occupancy, we now introduce a measure that captures the non-injectivity of a map. We call this measure the excess area. It is defined as the difference between the total unsigned area of the mesh and the occupancy of its boundary. We can show that excess area is greater than both the area of overlap between triangles and the area of inverted triangles. It is smaller than the sum of both. This means the excess area is 0 if and only if there are no overlapping triangles or inverted triangles. In other words, this is a measure that captures the non-injectivity of a map. Here we show a few simple examples that illustrate the different quantities we used. Observe that the excess area captures both the area of overlapping between triangles as well as the area of inverted triangles. However, we cannot directly optimize the excess area because this measure can be non-smooth. In fact, each of the two terms in the excess area has non-smoothness in some generic configuration. For example, the unsigned area is not smooth as the triangle transitions from an inverted state to a non-inverted state, and the sharp change happens when the triangle becomes degenerate. For occupancy, it's not smooth when the map transitions from an overlapping state to a non-overlapping state, and the sharp change happens when the boundary edge coincide. The important thing to notice is that the non-smoothness happens in generic configuration during the map transition from a non-injective state to an injective state. To smooth the excess area, we will propose a smoother version for each of these two terms. To smooth unsigned area, we use an energy that we introduced in last year's SIGGRAPH. It's called the total lifted content. It measures the area of triangles not in 2D, but in a lifted 4-dimensional space. The lifting is defined by concatenating the 2D coordinates of each vertex with the coordinates of an additional triangle called auxiliary triangle into 4-dimensional coordinates. The lifting is controlled by a parameter alpha, which also controls the smoothness of the energy. When alpha is 0, the total lifted content is the same as the total unsigned area. As alpha increases, the energy becomes smoother. The idea of smoothing the occupancy is to avoid boundary edges coinciding. We do that by replacing each straight edge with a curve. In our case, the curve is a circular arc, whose center angle is theta, which is a constant parameter for every arc. We define the arc occupancy as the difference between the occupancy of the new curve formed by these arcs and the total area bounded by each edge and its arc. The arc occupancy is smooth almost everywhere, except when the arcs coincide, which rarely happens during the transition from an overlapping to a non-overlapping state. Here, the theta angle also plays a role of controlling the smoothness of the energy. When theta is 0, it's the same as occupancy, because the arcs become straight edges. As theta increases, the energy gets smoother. Finally, we define our energy, the smooth excess area, as the difference between the two smooth terms, the total lifted content and the arc occupancy. The energy is controlled by two parameters, alpha and theta. We show that for any positive parameters, this energy, just like the excess area, is greater than both the overlapping and the inverted area of the map, so it captures non-injectivity. Although larger alpha and theta leads to smoother energy, we show that for sufficiently small alpha and theta, the global minima of the energy is guaranteed to be locally injective, and its overlapping area is bounded by an arbitrarily small constant. However, in practice, injectivity is not guaranteed because alpha and theta value needed by the theoretical guarantee may be unfeasibly small, and a gradient-based solver is not able to find a global minimum of this non-convex energy. Nonetheless, we found that minimizing the energy using an off-the-shelf gradient-based solver with a reasonably small alpha and theta is quite successful in recovering global injectivity for challenging real-world examples. In our experiments, we use an off-the-shelf quasi-Newton solver. We terminate the optimization when the map becomes globally injective. To check it efficiently, we adopt the criteria by Lippmann, that is, a map is injective if and only if there are no inverted or degenerate triangles or boundary intersections. We also terminate the optimization if it has not converged to a local minimum after a maximum number of iterations. Next, I will show some results of our method. We start with a simple handcrafted example. This initial map has two positional constraints. It also has two inverted triangles and two boundary intersections. This example is created by dragging one corner of a square to a far away location. We first show the result of optimizing a non-smooth energy by taking the difference between the total lifted content and the occupancy. The occupancy is not a smooth energy as we have explained. As a result, the optimization gets stuck when two boundary edges coincide. In contrast, by replacing the occupancy with arc occupancy, the solver can proceed and successfully find an injective map. Notice for realization purpose, we pick a large theta value. However, in the rest experiment, we'll use a smaller theta value in order to find the injective maps for more challenging examples. Here we show a more complex handcrafted example. The initial map is created by dragging a few vertices on a denser square mesh to far away locations. This creates more inverted triangles. However, even for this very challenging example, our method is able to find an injective map. Here we are using a smaller theta value to ensure injectivity. In contrast, existing inversion-free methods, such as large-scale bounded distortion map, LBD, and simplex assembly, SA, are able to remove inverted triangles, but they cannot resolve overlap triangles. And this results in both overwound vertices and boundary intersections. We have constructed a large-scale benchmark dataset with thousands of real-world and complex examples. In each example, a source mesh is mapped to the plane with up to 20 positional constraints. The initial map are created by a wrap, which often contains many inverted triangles, overwound vertices, and global overlaps. For our method, we use the same alpha and theta parameters throughout the experiment, and we compare with the inversion-free methods, LBD and SA. Here we show the success rate of each method in creating maps that are free from inverted triangles, that are locally injective, that is further removes overwound vertices, or globally injective maps, which do not have global overlaps. Observe that our method significantly outperforms the inversion-free methods in achieving injective maps and achieves a globally injective map for more than 85% of the benchmark example. Next, we'll look at some concrete successful and failure examples. In this example, the initial map contains lots of inverted triangles, overwound vertices, and global overlaps, and boundary intersections. Our method successfully find an injective map by optimizing our smooth excess area energy. We zoom in the region where the boundary is getting very close to each other, but they do not touch. Neither LBD nor SA was able to remove all the inverted triangles, even though they are designed to do so. In addition, overwound vertices and boundary intersections remain in the map. Here's another example. The initial map has many thin needle-like parts poking into the mesh, which causes some narrow overlapping regions and many boundary intersections. Our method can still successfully find an injective map. The zoom in shows the overlapping is resolved and the boundary doesn't touch. In contrast, neither LBD nor SA was able to find an injective map, and a large area of overlapping remains in the mesh. Our method failed to find an injective map for about 15% of the benchmark example. For most of them, the solver has not converged when the maximum number of iterations are reached. We find a very common configuration that causes the slow convergence. That's what we call the crossing arm configuration. It is where the different parts of the mesh cross over each other. And in this case, to minimize the overlapping area, our method can result in a mesh that shrinks the crossing region to a point, making it difficult for each part to retract from the other part. In summary, we have proposed the first method to compute injective mapping starting from a non-injective initial maps while satisfying positional constraints. Our method significantly outperforms inversion-free methods on a large benchmark dataset. The core contribution is the new energy, smooth excess area. The energy captures both inverted and overlapping areas. It's sufficiently smooth to support gradient-based optimization, and the energy has theoretical guarantees of injectivity at its global minimum. The crossing arm configuration causes optimization to slow down. One way to improve the convergence rate is to use high-order Newton-type solvers. However, this requires our energy to have higher-order smoothness. Extending our energy to 3D is also an exciting future direction, with applications like volumetric mapping and 3D deformation. Thank you for attending this talk.